Hi friends, now we'll see some numericals on Hall effect. That Hall effect and that thing we have already completed. So in this numerical we'll see some basic terms related to this Hall effect that we should know, that dimensions along which the current is applying, along which magnetic field is applying, and in which direction we are getting or generating electric field. It is important thing. So first we'll see first numerical related to Hall effect is a strip of copper of thickness 1.5 into 10 raised to minus 4 meter is placed in a magnetic field of 1 Tesla perpendicular to plane of a strip, and a current of 10 ampere is set up in the strip. I'm repeating again. A strip of copper of thickness 1.5 into 10 raised to minus 4 meter. The thickness is given. This is the thickness. In magnetic field of 1 Tesla perpendicular to the plane of strip, and current of 10 ampere is set up in the strip. What will be the voltage will be appear across the width of strip if the concentration of charge carriers in copper is 8.5 into 10 raised to 28 electrons per meter cube. So here see, the magnetic field 1 Tesla is given, then current is 10 amperes given, charge concentration 8.5 into 10 raised to 28 electrons per meter cube given, and we have to calculate Hall voltage in that strip. So first we write what are given. The thickness of copper strip is 1.5 into 10 raised to minus 4 meter. Then strength is 1 Tesla and current is 10 ampere. Then concentration of charge carrier is given. Then we know the formula of Hall voltage, which is V suffix H. V suffix H is equal to R suffix H into Bi upon D. That we can write these RH in different form. This is 1 upon Q or 1 upon E. Why we are writing these in 1 upon Q form? Because in this numerical Hall coefficient is not mentioned. So ourselves we have to calculate Hall coefficient also, because here N is given charge concentration and the value of charge either Q or E we already know. So by substituting these, where we know these, B is 1 Tesla, so 1 is 10 ampere, so it is 10. Then this N is 8.5 into 10 raised to 28. Then value of these E is 1.6 into 10 raised to minus 19, and thickness of strip is given 1.5 into 10 raised to minus 4. Now just we have put this value. When you calculate it, that time we get the answer. That answer is VH is equal to 4.902 into 10 raised to minus 6 volt. So we are getting the Hall voltage by using this formula. Note that when Hall coefficient is not given in a numerical, that time we can calculate this Hall coefficient by this 1 upon NQ or 1 upon NE. Okay. Now we'll see next numerical. Next numerical is a copper specimen having length 1 meter, width 1 centimeter and thickness 1 mm is conducting a current of 1 ampere along the length. So current is along the length. A specimen is kept in magnetic field of 1 Tesla along the thickness. Magnetic field is along the thickness. It experiences Hall effect and Hall voltage 0.074 microvolt appears along its width. If conductivity of copper is 5.8 into 10 raised to minus plus 7 ohms meter inverse, find the Hall coefficient and mobility of electron in specimen. See again in numerical, the length is given, length is 1 meter, along that length current passing, that current is 1 ampere, then width is 1 centimeter, and there is along the width 0.07 microvolt, uh, that's volt Hall voltage generated, then thickness is 1 mm, along that thickness 1 Tesla of magnetic field is applied. From these given terms, we have to find Hall coefficient and mobility, that is R suffix h and mu is to calculate. So first we'll write given L is 1 meter, then these D is width is 1 centimeter, T thickness is 1 mm, and we convert it in one standard form, SI form. So 1 centimeter we can write 10 raised to minus 2 meter, thickness 1 mm is 10 raised to minus 3 meters, then magnetic field is 1 Tesla is given and current is 1 ampere. Now we have given Vh, that is Hall voltage, which is 0.074 into 10 raised to minus 6 volt, and in this case conductivity also given, which is 5.8 into 10 raised to 7 ohm meter inverse. So we'll use it to calculate mobility. First we calculate the Vh, that is Hall voltage, which is RH, that is R suffix h into BID upon A. But in this numerical, Vh is given, that is Hall voltage is given, and Hall coefficient is not given, or it is to calculate. So we can modify this formula in terms of Hall coefficient. So it will give R suffix h is equal to V suffix h into A upon BID, where A is the cross section area, B is the magnetic field, I is the current, and D is the width. So Hall coefficient will be 0.074 into 10 raised to minus 6 into 10 raised to minus 2. This is the value of width and this is value of thickness, 10 raised to minus 3 upon this B is the 1 Tesla, then current is 1 ampere, and this width is 1 centimeter. So when you calculate this by using scientific calculator, you will get the value as R is equal to 0.074 into 10 raised to minus 3 to minus 9 meter cube per coulomb. This is the value of Hall coefficient. Now, as we know the value of Hall coefficient, we can find the value of mobility. So, mobility of electron is given by mu is equal to sigma into RH, where sigma is conductivity and R suffix h is Hall coefficient. So, which is now just we have calculated this RH. So value of conductivity is 5.8 into 10 raised to 7 into 0.0074 into 10 raised to minus 9. When we calculate this by using calculator, that time we'll get the value of mobility as mu is equal to 0.4292 into 10 raised to minus 2 meter square upon Volt second. Next numerical, a specimen having length 1 centimeter, width is 1 millimeter, thickness 0.1 millimeter is made to conduct with 1 milliampere current and is placed in magnetic field of 1 Weber per meter square acting along the thickness. Calculate the Hall voltage in case of N type semiconductor with Hall coefficient minus 3.44 into 10 raised to minus 8 meter cube per coulomb. Second case, aluminum with Hall coefficient minus 0.3 into 10 raised to minus 10 meter cube per coulomb, and which of this material is more sensitive to Hall effect and why. I am repeating this again. The length is 1 centimeter, width is 1 mm, thickness is 0.1 mm, where along that length current is passing which is 1 milliampere. Then magnetic field is 1 Weber per meter square. See this 1 Weber per meter square. So this unit Weber per meter square and Tesla is equivalent. So instead of Weber per meter square, we can write Tesla also. Then we have to calculate Hall voltage in two cases. One is N-type semiconductor and second is aluminum. And then by comparing their value, we have to justify it which is more sensitive. Okay, so first we'll write the given things. Uh, Here width is 1 mm, then area is width into thickness, so that we have calculated directly. It is 10 raised to minus 3 meter into 0.1 into 10 raised to minus 3 meters, which gives 10 raised to minus 7 meters square. Then current is 1 milliampere, magnetic field is 1 Weber per meter square. So we'll start directly for N-type semiconductor. First, we'll calculate for N-type semiconductor, in which case we have given Hall coefficient, which is minus 3.44 into 10 raised to minus 8 meter cube per coulomb. So VH is the formula is RH into BID upon A. So VH we can calculate by putting the value of RH is minus 3.44 into 10 raised to minus 8. Then B is 1 Weber per meter square. Current is 1 milliampere. Then this width is 1 mm and cross section area is 10 raised to minus 7. So when we calculate this, we'll get the value which is minus 3.44 into 10 raised to minus 7. This minus 7 we can shift the decimal and these write as minus 6 volt, that is microvolt. So it gives 0 minus 0.344 microvolt. Next, for aluminum, just we have given these Hall coefficient, then same we'll put the value in same numerical and find the answer. That time we'll get the value is minus 0.003 microvolt. From both values of Hall voltage, we can tell that comparing the value of VH N type semiconductor is more